Hey, welcome back to Learn a Lottle. My name's Nate, and in this video we're going to derive the area of a circle, the surface area of a sphere, and the volume of a sphere. I can still remember when I first learnt about these equations. Now remember class, the area of a rectangle is A times B, so that for a prism, the surface area is adding up each of the rectangles, and the volume is A times B times C. Oh yeah, that made a lot of sense. I love that about maths. And we learnt that the area of a circle is pi r squared. And for a sphere, the surface area is 4 pi r squared. Hang on, I can make this work. And the volume is 4 over 3 pi r cubed. 4 over 3? What? You just have to remember that one. They didn't make much sense to me at the time, and we weren't expected to learn integral calculus before we learnt the volume of a sphere. But it is a very enjoyable experience to finally make sense of that piece of maths that we've known for years, but never really understood. So, without any further ado, let's get into it. Our starting point for these derivations is going to be the definition of the circumference of a circle, which is that the circumference is equal to pi d, where d is the diameter. And the diameter is 2 times the radius. So we have c is equal to 2 pi r, where r is the radius of the circle. And we're allowed to start here because this is actually the definition of pi. The value of pi, 3.1415, so on, this irrational number, very fascinating number, is defined as the ratio between the circumference and the diameter. So it is defined to be c over 2r. So we're allowed to start here without proving anything because this is true by definition. So now we're going to derive that the area of a circle is pi r squared. And in fact here I'm going to consider a circle of radius capital R. And the way we're going to determine this area is we're going to take a continuous sum of area elements. So I'll show you what one such area element looks like. So one area element is going to have a radius r, and it will be a circle of radius r, but it has a tiny bit of extra length dr. Yeah, so it's infinitesimally thin, but it does have a bit of thickness to it, essentially so that instead of it being a line, it is in fact an area. So this is my area element, dA. So the D really standing for differential, or really it just means a tiny chunk of area. And to calculate the area of a circle, we're going to integrate over these area elements, where integration is this idea, this mathematical formalization of this idea of a continuous sum. So we're going to determine this area via a continuous sum of area elements. So an area element is dA, and we'll notice that it's infinitesimally thin, which means it's almost essentially a circumference. So we're kind of adding together infinitely many circumferences to build up an area. So that's why we started with a reminder of the circumference of a circle. So the area of our area element dA is going to be 2 pi r, the circumference of a circle, times dr. So times that little extra amount of width. So A is the integral from 0 to capital R of dA, meaning we're going to be adding together infinitely many, infinitely thin circumferences, which I'm trying to draw here. Kind of adding together infinitely many of them, starting with that, starting right in the center where the radius of the circumference is 0, and ending up right at the edge where the circumference is at a radius of R, capital R that is. So we're adding together all these circumferences from a radius of 0 to a radius of capital R. So we have the integral from 0 to capital R, 2 pi r dr. We can pull out that factor of pi, and we know that the integrating 2r will give us r squared, and that is from 0 to capital R, so we get pi capital R squared. So the area of a circle is pi capital R squared. That's a circle of radius capital R. To determine that the surface area of a sphere of radius capital R is 4 pi capital R squared, we're again going to consider a continuous sum, where this idea of continuous sum is integration, the tools of integration of area elements. And again, for our area elements, we're going to use circumferences as our main tool, as our kind of starting point. But they're going to be a bit more complicated now because we have to take into account 3 dimensions. So it's going to, it'll be a bit more complicated than the circle example, but we'll go through it and hopefully it'll all make sense. So I'll show you again what an area element will look like. So here is my area element, and it might be a bit hard to see from the picture, but the idea here is if you imagine a ball, maybe a tennis ball, I've wrapped around a rubber band around some part of the tennis ball. So this is my area element. And again, this area element has a tiny amount of width so that it's an area. And I'm going to call this width ds because it's kind of a tiny chunk of arc length around the sphere. So if you imagine a tennis ball or a small kind of beach ball, and I've taken a rubber band and wrapped that rubber band around at some point or at some height around the ball. So depending on the place I've wrapped it around, I could have wrapped it towards the top up here, or I could have wrapped it around the equator, you might say, of the ball. Depending on where I've wrapped this rubber band around, I'm going to have a different radius for this circumference. So if I consider this kind of triangle I've broken down, so going from the center of the sphere to any point that my area element is, and I consider it kind of makes this angle theta with the axis, the horizontal axis, and the hypotenuse of this triangle is capital R because that's the radius of the sphere. And the radius of my circumference, my area element, my circumference, is little r down here. So I have that little r is equal to capital R cos theta. That will come in handy. So what I have is that my area element, my surface area element, which maybe I'll call ds in this case, instead of dA, it's ds, an element of surface area. is equal to, again, 2 pi little r, which is going to change depending on that angle theta that I make, times d little s, that little chunk of, that little amount of width, the width of the rubber band, you might say. So here I need to make an observation that this ds actually has a relationship to d theta and r. So if I imagine a tiny chunk of angle d theta, because really what I'm going to do is I'm going to add up a whole lot of these rubber bands. So I might, I'll take that one and then that one, and then I build up the surface area of the sphere by adding up these infinitely many, infinitely thin rubber bands wrapped around the ball. So for each rubber band, there's going to be this little width ds, and really that's going to be an arc length subtended by a little angle d theta. And I'm actually going to end up integrating over d theta because ds I can't really integrate over. It's not as clear what I need to do there. And of course, because this ds is along the surface area of the sphere, this is radius r. And this is also radius r. And what I get is, by the definition of radians, so I'm going to have to use radians for these angle thetas. And this is kind of why radians are used in calculus, as opposed to degrees, which are a bit of an arbitrary measurement for angles. We just decide a revolution is 360, essentially because it's a nice number. It divides into a lot of different integers. So, on the other hand, radians are defined as the ratio between the arc length subtended by the angle and the radius of the circle. So, I'll write the definition of radians tells us in this case that d theta in radians is defined to be the ratio between ds and capital R. So what I get from this is that d little s is equal to r d theta. So this tells me that my element of surface area is 2 pi capital R cos theta, because little r is capital R cos theta, times ds, which is capital R d theta. So my integral over surface area is going to be 2 times the integral from 0 to pi on 2. Basically because considering this angle I'm using for the different heights of rubber band I'm wrapping around, I'm adding up all these rubber bands. If I let theta range from 0 to pi on 2, a right angle, I will only cover half the sphere. So the surface area of the whole sphere is 2 times this integral. So I get 2 times the integral from 0 to pi over 2 of 2 pi capital R squared cos theta d theta, which is equal to 4 pi capital R squared integral from 0 to pi over 2 of cos theta d theta. So S is equal to 4 pi capital R squared. And then if we integrate this, cos theta integrates to sine theta. So upper terminal of pi on 2 and a lower terminal of 0. That means we're going to have sine pi on 2, which is 1, minus sine 0, which is 0. So we're left with the surface area is 4 pi capital R squared, which is what we were after. So this way of using calculus, adding up these area elements and then considering, crucially, the geometry of those area elements, by doing this, we actually recover that formula, 4 pi r squared, which really confused me when I first heard it, because how on earth do you make a sphere surface area out of 4 circles? Well, apparently this is how. So now we'll move on to the big one, the volume of a sphere. Now, if you've been following along so far, you may see where we're going to go with this. The elements we're going to add up this time slightly different, because instead of developing an area, a two-dimensional part, we're going to develop a volume, a three-dimensional quantity. So we're going to be adding up area elements. We're going to be adding up volume elements that are made from an area, as opposed to previously we were integrating area elements which were really made from a circumference, which is a one-dimensional quantity. It's just the length of a line. So our element in this case is going to be the surface area of some sphere. So I'll draw up my sphere. There we go, there's my dodgy little sphere sitting in there at some radius little r. And again, this is going to have a little bit of thickness to it. So it'll be kind of dr. So I'll just shade that in. So that's an infinitesimally thick, a kind of shell. So maybe we'll write, so in order to develop this formula, we're going to take a continuous sum of, let's call them shell volume elements. So our volume element will be 4 pi little r squared, our surface area for a sphere, and then dr, a little chunk of extra width to that shell. So it's no longer a flat surface, it's got a little bit of thickness to it, so it is a volume. And then we're going to develop our full volume, integrate that from 0 to capital R, dv, our volume element, so 0, capital R, 4 pi r squared dr. So we get 4 pi and then r cubed on 3, 0 to capital R, and we gain that formula and find out once and for all why on earth there is a 4 over 3 in the equation for the volume of a sphere. So there you go.